our in-person session. So a couple of things to think about. We have a bunch of people who have already told us that they're going to be able to join us. So here is the list of people that we have that have completed their in-person registration. So all of you people I know are coming for sure, and I'm pretty sure more of you are coming that I don't have on this list that I've talked to. So if for some reason the paperwork is lost in the silliness that is the web, you'll be getting an email from me this afternoon. And if you've already sent the paperwork, just accept my sincerest apologies and I will get it taken care of. Even if I don't have you on this list, there's still plenty of room for everyone who's coming. We have room for everyone. So what are we going to be doing? On Monday, we're going to have coffee and check-in at 9. We'll officially start at 10, so if you're flying in on Monday, don't worry, you'll get here in time. We'll have small group work at 10:15, so each of you is going to be assigned to a small group for this year. Most of my cohorts have told me that that's actually the most important thing they've done the whole year, so you actually have some time in your small group. Then we're going to do a time management seminar with Dr. Mary Ottolini, and then we're going to go have some fun. So we're getting on a shuttle bus. Yes, we are taking the short bus to Capitol Hill. So we're going to go and have lunch on the mall because that's where all the good food trucks are, and I decided that was by far the easiest way for all of you to choose what you wanted without me having to make the choice for you. Then we have a Capitol tour. We're meeting with healthcare advocates who have been involved in things like the 21st Century Cures Act and other kind of rare disease specific advocacy programs. And then we have time down on the mall. So the Air and Space Museum, the National Gallery of Art, Portrait Gallery, all those things are open in the evening, so you guys can hit a sightseeing place, or you can head back to your hotel and be boring, whatever you want to do. And then on Tuesday, we start again at 9. We're going to have you do a 1-minute description of your work. We call these our elevator talks. So literally, you have 1 minute, and we want you to talk to us like we are 6th graders. I know that sounds really stupid, but most people understand what we do at the 6th grade level. So we want to have you tell all of us what you do in 1 minute. And we will have people there to give you some feedback, and we'll be giving each other feedback on that, and all of that is on LearnRD if you have more questions about that. Then we'll be doing just a lunch session, and then we'll be doing some writing talks of how to be more successful in writing. And then we'll do a 1-year timeline. We actually want you to sit down and go through what are your goals for this year and how do we need to get from point A to point B. And finally, we'll talk about some of the sessions that are happening in fall and what those are going to look like. So we're excited that all of you are coming into town that can come. There are a few of you that cannot head into town. Don't worry. We have an entire group of people that can't make it into town, and they're actually going to do a little session on their own. So we are looking forward to having all of you with us. So that was you're coming soon to see us. And now I'm hoping, Gary, are you there? Can you hear us?
I am.
Oh, thank you so much. So you guys have to accept my apologies that I sent the link to the wrong email address earlier today. So yay, he got on and he's now linked in with us. So I have to tell everyone, I was so excited. I went to a meeting in San Francisco last year, and Dr. Gary Dallaghan was presenting on statistics, and I was sitting there, and I should have been focusing on my own research, and I was not, I'll be honest. I was sitting there thinking, I wonder if he'd come talk to my rare disease scholars. I wonder how I can get him to do this. What bribery do I need to have him do this for me? And I'll be honest, it took very little bribery, and I just can't be happier that you took some time out to stop what you do on a regular basis and give us the chance to kind of share with us more about how we should be thinking about statistics in a different way. So I'm putting you as presenter, so you should be able to click on the blue circle in the middle of your screen now, and there you go. We already can see you. So take it away, and if there are questions as we go, I will bring them up if you type them into the chat. And otherwise, thanks so much for joining us.
All right. Well, Deb said, my name is Gary Dallaghan. I'm Assistant Dean for Medical Education at the University of Nebraska, and I am an Associate Professor of Pediatrics here. I actually started in the Department of Pediatrics in 1997, and I was the clerkship administrator, and I've kind of worked my way up over the years to where I'm at today. So my background is in educational psychology, so some of the examples I'm going to be giving you guys relate to education, but really anything where stats are concerned, you can apply to any type of research that you're doing. So just so we have this right up front, there are no conflicts of interest to disclose. And I'd like to acknowledge the group that initially helped give this presentation at ComCep in 2016 was where we started off, and have since been doing this for the Education Scholars Program at the Pediatric Academic Societies meeting. So the whole gist of this talk is really to help give you guys an understanding of statistics. It's not to help you know how to do statistics. You know, it's one of those things that I know stats can be kind of frightening for most people, and I think a lot of it comes back to who you had as an instructor at one point in time. They probably scared the bejesus out of you, so you don't want to deal with it anymore. But we're just going to talk a little bit about the importance of the research question and how that relates to your hypothesis statements, and then how that translates into choosing variables that you're going to be using when you're actually later on doing the analyses, and how all of these things really tie together. So it's a whole iterative process, but it's really important to just understand that whole process. So when you're starting with your research, you always start with an argument, and so you know, it's important to think through your idea and through your research argument, and you're looking for what's wrong. You know, is there some problem that you're trying to solve? Is there something unique that you've identified that needs to be investigated in some way, shape, or form? And then it's really important to go out and look in the literature to see, has anybody else found this same issue and reported on it? And if they have, how is what you're thinking about different? So that way you can fill a gap in the literature in some way, shape, or form. So most of you, I'm sure, are well aware of that whole process. So there are different types of research questions. They're exploratory, descriptive, explanatory, and they each seek to solve a different problem. You know, so an exploratory one, you want to gain an understanding of a new topic. Descriptive, that helps you to present a portrait of a specific situation. So a lot of times if you think of case studies, that's more of a descriptive study. Explanatory ones answer why, and you identify reasons why phenomena occur, and a lot of times those why questions are related to truly experimental types of research. So these are just some examples from the literature for educational research that I found that we like to use as examples, so that way people can get a sense of what these research questions look like. So, you know, you've got which of the two teaching methods is more effective at increasing students' recognition and assessment of common ethical dilemmas. That's a mouthful, but it's more of an exploratory one, looking at two different teaching methods. The descriptive one is looking at a relationship between student burnout, empathy, and professional climate. And in an explanatory one, they want to know how in-training exam predicts performance on general pediatric certification examinations. So the components of a research question really, like I said, they help you to identify what your variables are when you're looking at statistical analysis. And so when you're looking at major outcomes, the outcome that you're looking for is the dependent variable. And that's the thing that should be influenced by whatever experimental types of things you're doing, or if there's other outlying variables that you're considering. So the intervention is the independent variable, and that's what you're actually applying to that outcome that you're looking at. So for us in education, it would be looking at, are these E-modules impacting students' knowledge and retention? So you're looking to see what sort of exam results are coming, and then if you tested them later on too, is there still retention just because you utilized a different teaching modality? You know, and so you're always looking at some of these things as a difference or a relationship, and that would help you to know what statistics you're going to be using. And you look at the population that you're applying all of this to. And so all of these things really coalesce around what is in your research question, or ultimately what type of hypothesis statements you may come up with. So here's an example from a research project that we did here several years ago in pediatrics. Oh, excuse me. So when I started working on my PhD, one of the articles that I ran across that we had to review for class dealt with interest in mathematics, and I had a strong interest in that because my master's degree is in mathematics. So I was reading through it, and I thought that the tool that they developed for interest in mathematics would easily be translated into interest in pediatrics. And so we came up with a project where we could randomize the students into case study or case discussion groups, where one case group got to have, they just heard about the case, they talked through it, walked through it, just straight up pediatric discussion about it. The other group, we found out what the students were interested in going into and personalized the case discussion around what their interests were, so that way they could see how pediatric medicine interfaced if they were interested in anesthesia or radiology or something along those lines, just to get them perked up a little bit more. So that's the gist of what that study was about. So walking through things, if you're looking at what we were doing, our outcome that we were looking at was to see if there was an increased interest in pediatrics after those case discussions were done. So the interest in pediatrics scale was the dependent variable. Our intervention was those random case discussions. So, you know, the students were in those different groups. And we were, if we were considering differences or relationship, we were looking at pre-post differences in their interest in pediatrics. So we'd have them fill out the interest in peds form on day one of the clerkship, and then we had them do it again at the end after they'd experienced that intervention. And the group that we were looking at were junior students on the pediatric clerkship. So does that all make sense to people right now? So if you look at other information, so we drafted a research question that said, how do specialty-specific case discussions influence students' interest in learning pediatrics? So you can dissect that down by looking and seeing that the specialty-specific case discussions were the independent variable. The dependent variable was interest in learning pediatrics. Influence was what we considered as the difference or the relationship, and then the students were the target population. So that just shows you how you can take the research question and really tease out and pull out the different aspects of what you're going to need later on when you're analyzing your data. So at this point in time, does anybody have any questions about this stuff? All right, hearing nothing, we can move into talking about different variables. So the things that you have to take into consideration when you're doing a statistical analysis is what type of variable that you have. And that's critical for choosing the appropriate statistical analysis. Continuous variables are those numbers that go from 0 to infinity and there's nothing in between. So, you know, you look at something like weight as an example of a continuous variable, or temperatures, different things like that. Dichotomous variables are exactly that. There's two possible outcomes. It's either yes or no. It's, you know, typically we say it's male or female. So, you know, so you're looking at just a very discrete two-answer outcome. Ordinal variables, that's typically when you're looking at things and it relates to Likert scale. So if you're asked to strongly agree or disagree with something, those are considered ordinal variables. And so a 5 is different than a 4, is different than a 3, is different than a 2, is different than a 1. It's not a continuous variable, and you can't consider them like that. There's some rule of thought right now that if you're using a scale like that and you have a lot larger of a range, so if you had 10 items for your scale and asked people to rate something along those lines, you could potentially start using that as a continuous variable, but I haven't seen it used that much. And then finally, the nominal variable is it's basically you're categorizing things by name. So if you're looking at, you've got a patient population from clinics X, Y, and Z, then you could categorize your patients in that regard, and then you could compare them across sites, basically using that as a categorization, and that is a nominal variable. So when you look at the fact that research questions drive study design, you have study questions that want to describe or explore a group or a phenomenon. The study type, you could do something qualitative or quantitative. I haven't seen a whole lot of clinical trials or anything like that hit on qualitative research, and that's not the point of this one, but there are qualitative research methods that you could look into if you're interested in that, but that's essentially looking at getting patient stories and things like that you would further investigate. Quantitative types of studies that are descriptive in nature are something like cross-sectional or purposeful, where you have a selected sample. If you're wanting to test a hypothesis, then the study designs are experimental, quasi-experimental, single subject, or cohort, which are also causal comparative.
I want to show you this really quickly. This is happening right now, a brush fire by the freeway. This is in the Rancho Cucamonga area, and at last check, it looks...
Okay.
Muted.
Study design is because, again, this is another one of those things that helps to drive what kind of statistical analysis that you're going to use on. So when we're talking about analyzing results, I know it's very simplistic,
right?
but a lot of statistical analyses really, it just kind of comes down to two different things: knowing what variables that you've got and the study design. And it's important to know those things, so that way you're not the one that's going to need to know how to do the statistical analyses, but if you know what those things are and you know that those are the things you want to collect, then when you sit down with a statistician to talk to them about what you're doing, you'll have all that stuff laid out, so that way they can help walk you through some more appropriate analyses that you may not have considered. Before we get into some of this other stuff, I wanted to hit on some of the definitions that are brought up a lot of times when you're dealing with stats. Power is obviously when you see something that's reported and they've got a p-value of less than 0.05, that means that it's the probability that your test will find something significantly different amongst the groups that you're looking at. If people are reporting about a type 1 error, it means that that is a probability of incorrectly rejecting a true statistical null hypothesis. Type 2 errors, probability of incorrectly accepting the null hypothesis. The reason that those two items are important, type 1 and type 2 errors, when you're dealing with smaller numbers in your population or in your analysis,
Muted.
There's a higher likelihood that you may have one of these types of errors. And, and there's no getting around it sometimes, but there's analyses that you can do that will help to minimize it. But a lot of times the only way to really truly minimize the chance of having a type 1 or type 2 error is to just have a larger population size. But it doesn't mean that you can't forge ahead and do the analyses that you need to. You just have to make sure that you're carefully interpreting the results that you come up with. And then finally, effect size is the measure of the observed difference. And that really comes down to just standardizing the mean of the two different groups that you might be looking at. So you basically take the mean of the experimental group and subtract the mean of the control group, and then you do an estimated standard deviation of the control population, and that's what you divide into that, the difference between those two, and that will give you the effect size. So onward and upward. So this is probably the other critical thing that I always reinforce with everybody, is that when you're analyzing your results, the very first thing that anybody needs to do is to to see if you have a normally distributed result, because that's going to actually help you to know exactly which analyses that you can or can't do. The rule of thumb usually is the larger the better with your population that you're looking at and the results that you've got, so that way you are pretty much assured that you're going to have a normal distribution. But given the fact that you guys are dealing with much smaller sample sizes sometimes, it may be difficult to do that. There's a theorem in mathematics called the central limit theorem that essentially has proven over and over again that with a normal distribution, it can be assumed if you have 30 or more, you can fairly well assume that you've got a normally distributed population without running into too many problems. So, you know, so this is something to keep in mind, but it's just one of those things that you want to make sure that the statistician does, so that way you know for sure that your data is either normally distributed or it's not, and that will, like I said, dictate which analyses you wind up doing, which we'll get into here shortly. So I'm going to walk through some of the different study types that can be done and just talk about some of the statistical analyses that relate to those, so that way you have a better sense of which statistics you may want to use when you're analyzing some of your data. So with an experimental or quasi-experimental type of study, you know, you've got randomization, so you've got a control group, you've got an experimental group. The difference between the quasi-experimental and full-on experimental is that a lot of times with quasi-experimental, you know what population you're targeting, so it's a little bit more of a purposeful sample, but you still do some randomization as part of it, so that's why it's quasi-experimental. With the analyses that you're doing, if you've got two different groups that you're looking at, or you've got two different measurements that you've done, so if you've got a patient where you've done, or some kind of a sample where you've taken one sample at one point in time and you take another one, you know, 4 or 5 hours later, and just limit yourself to that, which probably isn't likely, but if that's what you do, then using t-tests is the appropriate method. And z-tests are what has been referred to in statistics a lot of times for smaller samples that are basically a difference between means of continuous variables that you've collected. But I read recently with some of the methodology stuff that using t-tests regardless of the sample size has been proven to be fairly accurate. But t-tests are used when, like I said, you've got either two groups and you're looking at just data that you're wanting to compare between the two groups, and that's it. If it's more than one group or more than two groups that you're looking at, then you would want to use something like an analysis of variance, and that really looks at probabilities of those sorts of things happening. And so it's a I like to refer to it as a t-test for multiple groups, basically, because that's about what it's boiling down to. And so getting into some of the non-parametric analyses. So if you've done the initial work of looking to see if your data is normally distributed, then you can use something like t-tests or analysis of variance with no problem. If when you're doing that analysis and you realize that your data is not normally distributed, then you use something that's referred to as non-parametric statistics. And there's some thought that it's weaker because using non-parametric statistics because you've got a smaller sample size or whatever. But the rule of thumb for me is the fact that if whatever you're doing and however you're analyzing it, if you're using the appropriate analysis for it, then your statistics are sound, and that's what people should be looking at more than anything else. So for non-parametric correlates to doing a t-test or an analysis of variance, they're referred to as Mann-Whitney-U or Kruskal-Wallis for independent groups, or a Wilcoxon-Sign test is for paired groups. And if you have quite a bit of categorized data or nominal data, with what you're collecting, you can use the chi-square test or the Fisher exact test. And those work with, the chi-square test works with normally distributed data as well as data that's not normally distributed. What you report for the non-parametric data is more the Fisher exact test, but it's essentially the same thing as a chi-square test. So for a cohort study or causal comparative type of thing, that's you're looking at similarities, or the similarities between the experimental methods. You've got independent group comparisons. And there's the comparative studies involve looking at differences based on variables that cannot be manipulated. So gender and ethnicity are the most common comparisons that you simply can't change. The statistical analyses that are done for these types of studies involve t-tests, again, which you can do to compare independent groups as well as the same group at different time periods. You can do the analysis of variance, and that, again, is you can analyze independent means or proportions of two or more groups. The ANCOVA is for correlated means of two or more groups that are matched for statistical purposes. And then the non-parametric analyses, again, are those that are the Mann-Whitney U-test, the Kruskal-Wallis, and the Wilcoxon-Sign test. So they're very similar in nature to experimental types of studies. So for single subject or case studies, in the case study, the investigation is with the specific group or single subject. In these instances, it's pretty straightforward because you're primarily reporting descriptive data. There may be instances where you would want to compare groups in a case study, so you could use t-tests, or you could perhaps look at some correlation analyses, which would involve Pearson's R if it's a normally distributed group. Spearman's Rho is correlation for non-parametric data. And oftentimes when you see reporting on case studies, it's usually the mean or the median, and confidence intervals and effect size really come into play a lot here as well. So the cross-sectional and descriptive studies, these studies involve determining if there is some type of relationship between measured or categorical variables. It's where you use correlation and regression models to determine the relationships. What's important to understand is that these do not indicate causal relationships. Typically, there are multiple other factors that may be involved, and this is a beginning step that results in following up with an experimental or quasi-experimental study. So the analyses that you use for this are correlation. This could be between just two variables or multiple variables. Typically, there is one variable that's considered the dependent or the criterion variable. The other variables may have a relationship with that. So, you know, and there are other complex forms of looking at some of these things as far as correlation is concerned, but you know, you're primarily looking at Pearson's R or, as I said, Spearman's Rho. With regression, this allows you to make a predictive statement about the relationship. The variables that are reported typically involve beta, which is either positive or negative, and this indicates there's a positive or negative result depending on how much you're doing. When looking at examination performance and anxiety scales, you may notice a negative relationship. The beta would be negative, and so the R value in regression models indicates that the percent of variance of predictor variables contribute to the dependent variable result. So if you see an R squared of 0.411 as it relates to anxiety with the exams, you can say that 41.1% of the variance in examination scores is related to anxiety. So if you have a negative beta that's saying their anxiety score goes up, their exam scores go down, then 41.1% of that variance you could say is associated with higher levels of anxiety. And that really that's how you want to report things. The only way that you could ever say that there's a, where with regression is concerned, that you would be able to say that you've got some kind of a predictive value is if it was truly an experimental study that you were doing. far too often with the way people report regression analyses is that they say that X predicts Y, when really it just means that if X is there, then there might be a higher likelihood of Y occurring, but you can oftentimes say that there's a direct result. So let's get back to the example that I gave you guys earlier with the interest in pediatrics. So with this study, we identified a problem, and the concept was sparked from reading the article in the Journal of Educational Psychology. And after looking in the medical education literature, there was very little that had been done investigating this concept. So the study was very much feasible. We had a clear goal in mind with the way the study was set up. We got IRB approval. And given the setup, the analyses that we ended up choosing where we looked at descriptive data, we realized that we should probably just do a t-test or ANOVA because we were comparing the experimental group versus the control group. And we ended up looking, when we looked at the data, what we found, since everything was basically done as a scaled item by item on that interest scale, we used the Wilcoxon signed rank test because we were looking at dependent groups, but because it's ordinal in nature, we couldn't do a t-test because that would mean that that data was continuous in some way, shape, or form. So if you look at something like this, and Deb, do you have this? Or have you shared it with them, the handouts that I had at PAS? Answer me. If you guys haven't gotten this yet from Deb, this is a handout that I put together for PAS, and I can share it with her so she can get it out to you guys. But essentially it takes and looks at different groups, whether it be independent groups or dependent groups, and shows you, based on the variable type, what kind of tests that you would run. So like I said, with our study, we had ordinal variables, so we used the Wilcoxon rank sum test. So now that we're at this point, this is the important stuff for what I understand you folks in the Scholars Program are interested in, because you have smaller N values for your clinical trials that you do. And so I wanted to hit on some of the different types of study or types of analyses that are maybe offered up or suggested to you when you talk to a statistician about doing some of these things, just so you have a good sense of what they are talking about. And so a sequential analysis involves analyzing data as it's accumulated with the goal of stopping collection once results become statistically compelling. So essentially, after each observation, the decision is made to continue the study by enrolling additional participants, or to stop the study because you've achieved significance or determined no significance will be achieved. So standard analyses with this would be probably using t-tests or ANOVA. But again, like I said, it's just one of those things where you're collecting data as you go along, and then you keep checking it to see if you've hit a certain power level or not with what you're looking for. Hierarchical models are useful for smaller data sets. This type of model provides a natural framework for combining information from a series of smaller data collections. And hierarchical models also provide a foundation for analysis of longitudinal studies, which are important for increasing the power of the research. And now these types of models employ different regression models to analyze the data. I've actually done some of these for some educational research, and had to teach myself how to do them because I'd never done a hierarchical model before, but it was a great deal of fun. The thing that I found with doing that, though, was even though it's a regression model and you get the results that you can analyze, ultimately you wind up going back and get a little bit more granular with the regression or correlation analyses that you were looking at before, so that way you can truly see where some of the significance came from. Bayesian analysis offers some flexibility, read subjectivity with its analysis. The data is collected related to the experimental and control treatments to identify what is identified as a theta value. There's an elegance to this approach. However, the notion of a subjective distribution often gives some researchers pause. But there are advantages to using this type of analysis, as it's easy to formulate problem formulation, sequential analysis, prediction, and meta-analyses. I've not had any experience with this. When I was reading more about it, it's essentially you as a researcher discuss what you think is actually going to happen and start building a model around that. It would take a biostatistician to really walk you through the process to understand that a little bit better, but if they bring up the idea of using Bayesian statistics, at least you have a better sense of what they're wanting to do. Statistical prediction involves obtaining samples sequentially from small clusters and comparing them to similar number of small clusters of a control group. So this would allow you to identify confidence intervals to use probability of falling within that interval. So a lot of non-parametric measures can be used, but as more samples are gathered, normal or log normal or Poisson distributions can be used for the probability models, which fit more in line with normally distributed data. And like I said, that whole process is basically you're looking to be able to predict that the data that you're collecting is going to fall into a particular confidence interval of where you expect the results to lie. And a meta-analysis involves a set of statistical procedures used to summarize empirical research in the literature. This is used a lot more in education and psychology because of the smaller sample sizes that people have in those areas. And so this is a way to look at a series of smaller studies collectively to enhance the power of collective findings. And you have to gather up a lot of the data from those studies that you're looking at and use different analysis techniques to put it all together in the long run and run some other statistics to identify if there's any significance to similarities. There's some drawbacks to doing that because you may not know exactly how the experiments were done in the smaller studies that you're looking at, but it's really, if you've talked to anybody who's done a systematic review of the literature, a meta-analysis is just a more enhanced, rigorous type of systematic review where they're actually really delving into the data that was reported. And
Can I ask you, do you mind if we go back for a second? Can I ask a question?
Yeah.
Hey, this is Deb. So for the sequential, I'll tell my own personal example of I was told we couldn't do sequential because that's as if you've unblinded your data. Have you had issues in small disease cohorts that means you would unblind your data too early, or how would you, is there a way to, I don't know, maintain your ethics of being blinded to your data and still do sequential in a meaningful way?
That I don't know. I'm not having experience with that. I honestly think that something along with a sequential analysis, I think a lot of times it's more along the lines that you're collecting data and it's not in a double-blind type of study.
Okay.
I don't know necessarily that you'd be able to do something, do a sequential analysis for something that's double-blind because you would run into the issue of having to unblind what you're doing unless you had somebody completely separate doing the analysis, then you weren't.
Okay. Or it might be useful in some type of like natural history, like a short natural history study or something like that.
Right.
Okay. Okay. Thanks. Okay. Thank you.
Other questions? So this final table is just, I put it together really as a breakdown just so you can see what the study design, the analysis type that you might use, and I included some of the variables that might crop up. So if you look at the randomized control row, and I've got a beta or R squared, that relates to the regression variables, and so the purpose is spelled out on the right-hand side. But I will be perfectly honest with you guys, I love doing statistics, but I don't get to do them all the time. I put this stuff together as a way to remind me every time I get ready to start working on some stuff, so that way I'm making sure that I'm not doing something stupid when I'm analyzing my data. You know, so if you don't live it day in and day out, and I don't, then having helpful things like this around is a good way to to help you to remember what you need to be looking at. And like I said, when you're doing some of these things, the critical thing is to think about the variables or the data that you're actually collecting and how that relates to your hypothesis statements or your research question. And once you have that figured out, then sit down with a statistician and walk through what you're going to be doing, and that way they'll have a better sense of this is where you need to go, and they'll offer other things to consider. Because like I said, especially for social science types of research, there are so many other things to take into consideration if you're looking at, is this intervention that I'm doing with the students to help them to learn the material better working? Well, you don't know everything that they're doing to prepare for an exam, so you've got to take other things into consideration, and so there's a lot of different things that may crop up, and a statistician can help walk through some of that stuff. And with that, I'm done, and I'm open to questions.
That was great. This is Deb. So if you have questions, go ahead and I'm going to unmute everyone. I'm always scared to do that. And I'll review people if it's really loud. But I'm unmuting everyone. So if you have questions, jump in here. I will ask Gary, can you tell me a little bit about when's the right time to find a statistician? And if you don't know how to find one, what's a good way to find one?
I honestly think the right time to talk to a statistician is right at the outset of what you're doing. So when you start putting together your, formulating your research ideas and the question that you've got, once you've pretty much nailed down what you want for a question, you've got some hypothesis statements that you may put together, that's the time to go talk to a statistician, just to make sure that the data that you're collecting is going to help you to confirm or refute your null hypotheses that you're coming up with. And it's also a way to talk to them to find out, you know, get a sense of perhaps what you might need for statistical power and whether or not you could ever achieve that. If you can't, like I said, there are analyses that you can do for smaller numbers, and that's the sort of thing that the statistician would need to know. So that way they're better prepared. If you don't have biostatistician-like people on campus or where you're at, it never hurts to contact, if you've got a local college, to contact somebody in their math department to see if there's a statistician that would be willing to sit down and talk to you.
Great idea.
You know, I know a lot of the faculty at our sister campus, which is halfway across town. They have been much more than happy to work with people here at the medical center. If you call them up and just say, hey, I'm doing this and I don't have a statistician around, is there somebody I could talk to? And they typically will be more than happy to walk through things with people just to get a sense of what you need to do. And, you know, I mean, knowing other people, too, that have done some research, that you might check with them to see who they actually talk to as far as a statistician is concerned. I've answered emails from people when they've had questions about stuff before, so it's, you know, I think there's a lot of opportunity out there, but, you know, if you don't have biostatisticians at your site, then I would definitely start with going to a local college to talk to somebody in their math department to see if there's somebody that could help out.
That's a great idea. And just so everyone on this call knows, since we do have oversight by the Rare Disease Clinical Research Network consortia, if you are doing something that falls under the consortia heading, we might be able to get you hooked up with a statistician through one of the consortia. So if you're feeling like, I don't know where to go, I'm desperate, I don't even know who to talk to, let me know, and let me see if I can find you some resources too. But I love that idea of going to an undergraduate math program. That's a brilliant idea. I love that. I'm going to pass that around. That's great. Anyone else have questions? Well, I can't even thank you enough. This was great. Thank you so much for taking time out and for chatting with us. And I was chuckling, I was born in Nebraska, so this is great, having someone from Nebraska. Just so lucky, thank you.
And I'm Kim Chapman, sitting right next to Deb, and I went to the University of Nebraska Medical Center for med school and got my PhD there. So
awesome.
You have huge Nebraska fans in the room, so we're just so thankful. And you totally lived up to my expectations. I so appreciate you taking time out to do this.
Not a problem.
And all the trainees on the call, we hope that this was a great experience. This will be recorded for those of you who are in clinic or at other places. If you have follow-up questions, feel free to email me, dregear@cnmc.org, and I will get them either to one of the people in the Rare Disease Network that can answer your question, or if there's a few similar questions, I'll forward them on to Gary for us. So thank you so much, everyone, and have a great afternoon. Thanks so much. Bye, all.
Bye.